Hello everybody. I'm trying to provide a few small lectures that help you to review the content covered in MECH215, particularly those ones that I covered in my sessions, because I consider that these are very important concepts that help you to understand the topic and as well as in your exams. If you find this video is helpful, if you want to know more information about certain other topics, please provide me some comments. If I got time, I will provide new videos. Maybe it's too late for you guys, but maybe it will be helpful for the next batch of students. And also, if you have questions about particular time during the video, you can also give me comments, and I can answer you through the either the comments or another video. So the first topic I'm going to talk about is the principal stress. So the reason we want to talk about principal stress is when we do the maximum shear stress theory. So maximum shear stress, tau max, is equal to half of sigma 1 minus sigma 3. So sigma 1 and sigma 3 is 2 out of the 3 principal stress. So what is principal stress? We need to understand that and be able to use this maximum shear stress theory. So the shear stress must be less or equal than half of the yield stress to be safe. Okay, so what is the principal stress? So in three-dimensional space, that's where we are, we have 6 stress components. Have sigma x, y, z. These 3 are the normal stress. And also at the same time we have the 3 shear stress component, tau xy, yz, and zx. So all these, any position in the component, you have these 6 components. However, if you rotate the coordinate slightly, you can turn that coordinate frame slightly differently, and there's always a certain orientation that you be able to get rid of all the other shear stress, make them all 0, and you only left with those 3 normal stress. And we call this situation, these are the principal stress because you don't have the shear stress. And we order these principal stress in a falling order. So sigma 1 is the largest of the 3, sigma 3 is the smallest of the 3, and sigma 2 is in the middle. So if we know these 3 principal stress, then we can use them to solve the maximum shear stress theory. Use maximum shear stress theory to solve the problem, the static loading problem. So eventually the safety factor, if I just simplify these, multiply 2 on both sides, the safety factor for the maximum shear stress is N equal to SY, that's the yield strength of the material. We always use yield strength here for the this non-brittle material. Okay? So we normally wouldn't use a brittle material to fabricate some shafts and components for our manufacturing. So we're always using certain non-brittle material. And the yield strength of the material over the sigma 1 minus sigma 3, these are the difference between the largest and smallest principal stress, will give us the safety factor in maximum shear stress theory. Okay? So I write this equation in kind of a few different ways, but they are all the same. So the first one, this one is showing the safety factor. How do we get safety factor? This one is when the system actually fails. So this question is applied to the tutorial question in week 1. So if you go check the tutorial question 5.1, we have a few kind of different situations, A, B, C, D, E, F. And we given sigma x, sigma y, sometimes we get a tau xy. However, we always missing a few other components, so we can assume the missing ones are all zeros. That's what we always start with. And in our actual case, if you remember the midterm exam, you have a shaft with certain loading. You have the normal tension. You have torsion. from a torque, and also you have a bending from another force. So the combination of those three external force and torque will eventually result in some normal stress, shear stress at the component. However, in those cases, even they combine together, we always got a planary situation. So you don't get sigma x, y, and z, all of them. You only got 2 out of the 3. So in that case, this planary case would be more useful for us to understand the issue. So this is a general case. You have normal stress, x, sigma y, and you have shear stress. So through certain kind of rotation with a phi. So in this part, in our subject, the value of the phi doesn't really matter too much. Not like in 251, you have to actually know what angle is actually got the principal stress. So the thing matters here is the value of the sigma 1, sigma 2, and sigma 3. And remember, this is a planary case. So out of this, we got 2 values from the 3. And remember, the third one is 0. So we have to rank these 3 in a order that from the maximum to the minimum. So this is the maximum to the minimum. So that's the biggest, this is the smallest. Okay? So sometimes when we solve this, we got sigma 1 and sigma 2. Sometimes we solve this, we got sigma 1 and sigma 3. Sometimes we got a sigma 2 and sigma 3. So remember, the other one is 0. We have to reorder them before we can go carry on to use this theory, because this one's the biggest and smallest. Over here, we get 2 out of the 3. We don't know which one is biggest or smallest until we compare that with the 0 value. Okay, so let's look at these 5 cases. So the question here is, we wanted to use the maximum shear stress theory to look at the failure condition, safety factor, with certain kind of loading condition. So so this one is question A. We get a sigma x is 100, sigma y is 100. We don't have tau here. So that means if there's no tau, they're all 0. And we didn't mention sigma z, so that's 0 as well. So this is already principal stress because there's no shear stress here in xy. There's x, sigma y, but in tau xy, there's nothing, there's 0. So that's already our principal stress. So we have the third one, sigma z is also our principal stress. So 3 of these values are 100, 100, and 0. So after we reorder them, so the largest one is 100, the middle one is also 100, the smallest one is 0. Then our maximum shear stress is half of the biggest minus smallest. So 100 minus 0, you get 50. Then use our safety factor formula. So Sy over sigma 1 minus sigma 3, and we get 3.5. Okay, so this is the case when you already given the principal stress, don't have the shear stress. And in our exam, we give you a formula table, so which ones are important. In this case, let's see, this ones. So this is when you have sigma x, sigma y, and also the r. R is our shear stress, basically, here. And how do we get sigma a and sigma b? So this is a little bit confusing because sigma a and sigma b is some books use them as the 2 of the 3 principal stress. You can have sigma a, sigma b, sigma c. So in this case, these principal stress is not in particular order. Then you write it as sigma 1, sigma 2, sigma 3. Then these 3 are in order of when sigma 1 is the largest. And the shear stress is calculated from this equation. So these 2 adding together, you can get your sigma a and sigma b. And by considering sigma c is 0, so you have a, sigma b, and 0. 3 things, you have to reorder them into a certain order. Then you can use this one to do the calculation. So sigma A 1 and sigma 3. So this sigma 1 and sigma 3 is picking from sigma A, sigma B, and 0, picking from those three numbers. So that's this question. So, so when you do the static loading maximum shear stress failing theory, this is how you address this question. Let's look at the question B. So in this case, you have sigma x equal to 100, sigma y equal to 50. Right? Again, the other things are all zeros. So we'll rewrite them. So we get sigma 1 is 100. This is the largest. Sigma 2 is 50. This is the middle one. Sigma 3 is 0. So our maximum shear stress is half of the largest minus the smallest principal stress. You get 50. So remember here, you don't use sigma 1 minus sigma 2, those two which coming from your calculation, because there's a 0 which is smallest. Okay, and again you use the factor of safety here to get 3.5. So the tricky part for this one is you don't use whatever you got from there directly in the calculation. You have to consider the smallest one is 0. Question 3. Question 3, you got sigma x is 100 and tau xy is negative 75. So what does this tell us is sigma y is 0. Oh, certainly the sigma z, things with z is all 0. So you got sigma x is 100, y is 0, and tau is negative 75. Again, we go to the formula table using these two. So what we know is we know the sigma x, we know the tau xy, and we know sigma y is 0. Putting there, we get r, and from r we get sigma a and sigma b. From the book, you can also find equation 313, 314. So that's where the equation come from. So a notice here is in the book use sigma 1 and sigma 2, but many other books use sigma a and sigma b. So the reason of sigma a and b is because we don't know the order of how big or small this value is. And also another better way to intuitively understand this problem is draw Moore's circle. So this part, if you don't understand, it's okay. Remember the things I just mentioned in the last few minutes. That's okay. But if you do understand, this will make things much easier to kind of interpret, and you don't have to memorize anything. This is basically you got 2 points on a circle and trying to solve a circle. Okay, so this is a Moore's circle we're talking about. So for example, the previous question, you have sigma x and sigma y equal to 0, and then you have tau xy equal to something. So basically you get 2 points on the circle. Normally it's a diameter. And from there, you know the radius of the circle, and you know the center of the circle. Then you can do the offsetting, and you use the Pythagorean theory. You can get everything. So this is the radius, is from the previous equation, and this is the center, is half of the sigma x minus sigma y. Then the actual sigma 1 and sigma 3 is the center plus and minus the radius. So that's just coming back to this equation. So that's this is your radius, and this is the center. Center plus minus radius is the normal stress, principal stress, sorry. So for example, we just got is if we only know sigma x 80 and tau xy is 50, the 2 points we're having is 80, 50, and 0, negative 50. Or you can have 80, negative 50, or 0, plus 50. These two cases are the same. Okay? So if you only know the sigma x and tau xy, you get 2 points. The reason is because you have the sigma y is equal to 0, so that's 0. So it's 80, 50, which is this point, and 0, negative 50. Okay? So this is your horizontal axis for the normal stress. This is your vertical axis for the shear stress. Okay? From these 2 points, you can find a middle point. Right? Because that's 50, that's negative 50, so middle point is on the horizontal axis. And the value is 40. Okay? 0 and 80, average is 40. Then the radius of the circle is basically you solve this triangle. Use Pythagorean theory. Right? Because this is 40, that's 50. So you can easily read from there. Then the radius 64. If you know the radius 64, so this is also 64. So this point is 40 minus 64. This point is 40 plus 64. So you basically can solve everything. Okay? But if you don't understand this Mohr circle, it's fine. You still be able to address this by using those 2 equations. So I mean, from exam paper, these 2 equations. You normally use this one first, then you do the other one to find the shear, the radius first, and the normal principal stress. Case C. So back to case C. We use these 2 formulas from the formula booklet. Okay, and put numbers in. So sigma x is 100, sigma y is 0, and tau xy is negative 75. Put in there, you get r, and you get sigma a, sigma b. All right, so I is actually, I didn't put in here, but sigma a and b is 140 and negative 40. So again, we get 2 out of the 3 principal stress. The third one is 0. So we order them into sigma 1, sigma 2, sigma 3 from the largest to the smallest. Our maximum shear stress tells us the difference between the biggest and smallest is our sigma 1 minus sigma 3. So use the yield strength divided by sigma 1 minus sigma 3, you got the factor of safety. Okay, so in this case, you have to use these 2 equations to address the principal stress. Case D. So this is a kind of more general case. You got sigma x, sigma y, and you also have tau xy. More general case. Again, we use this formula to get r first, then you get sigma a and sigma b. So in this case, what we got is negative 11 and negative 114. Remember, the third one 0. Then we rank them from the biggest to the smallest. Actually, 0 is the biggest. Negative 11, then negative 114. So the safety, factor of safety is equal to yield stress over the sigma 1 minus sigma 3. Okay, so the negative doesn't matter in here. Okay, so that's type or question D. Question E, you got sigma x, sigma y, and tau xy. So again, the same situation as case D. You put in this formula, you got 104 and 15. Those are 2 principal stress. And the third one 0. Okay? So you always write in this order. Okay? In case you use these 2 by mistake. Okay? You don't use these 2. You use sigma 1 and sigma 3. You don't use this middle value. Okay? So this 5 question is quite good. It covers kind of all the cases you might have in a plenary situation to get the principal stress. And once you get a principal stress, you order them from the biggest to the smallest, then you put that into the maximum shear stress theory. Okay? Then you can solve the problem. So the key point here is don't forget, even in a plenary situation, all our object, all our components is always in three-dimensional. So the third one is always there, it's just 0, so it just didn't mention it. So most common one, you have something like this. That's very common situation. You have one direction with a normal stress and one have a shear stress. And once you got the principal stress out of this, you have to make sure add another one into it. Then rank them, then use the formula. So in the book or in the lectures, we mentioned a way of looking at into quadrants. So basically we have three cases. If the sigma A and B both larger than 0, so basically our larger one of the two, so in this case sigma A is our limit. The reason for that is because the other one is 0, so we use sigma A minus 0. That's our limit. So basically that's sigma A. That's this one. If sigma B is larger than sigma A, then sigma B is our limit. Okay? So that's why we got a kind of a square box in quadrant case 1, sorry. And the same thing for case 3. If you have both of them negative, you have the smallest one is the smaller negative one. So that's case 3. And the other one is 0. So you use the 0 to minus that. It's exact same thing as in the first quadrant. It's basically one is tension, one is compression. Case 2 is when we have one of them is positive and one of them negative. So sigma A is positive, sigma B is negative. So then we have to use the difference between sigma A and sigma B. Because the third one is 0, right in the middle, so we pick these two to compare with yield strength. Actually, there's case 4 over here. This is when you have sigma B larger than 0, larger than sigma A, and they are symmetric. So basically, they are the same case. You can look at this for comparison with the distortion energy method a bit later. So you can see this is always more conservative. So the N we got from maximum shear stress theory is always smaller, a little bit smaller than the distortion energy theory. Sometimes then at these corner points it can be exact same, but normally a little bit smaller. Okay, so this is the first topic to look at the static loading condition. What's the safety of factor and what's the failure condition when you have a plenary stress. So that's normally what you're going to have. For example, in the midterm exam, the second part you need to do is after you analyze the stress conditions, you just need to look at the principal stress, then use this equation to find the safety factor. So this is the end for the first video. I don't want to make this very long, so you get very bored to watch this. But do provide comments if you have any. Thank you.